Okay, here's some more of the Lagrange problems. This is number 3, and we want to find an approximation for the square root of 1.2. So I just let f of x be the square root of x, and I was going to find p sub 4. We want to find the fourth degree Taylor polynomial. So I chose a square root of x about the center of 1, or a equals 1. And it kind of makes sense because this is pretty close to 1. You could have done the square root of x plus 1 at a equals 0. That would be the same thing. It shifts it over, and you end up with the same, actually the same approximation and the same error. So either way, it would work out. This is a little easier to take the derivatives, but then the polynomial is a little more complicated. So, you gain in one, you lose on the other. All right. So first of all, I took my derivatives. So I'm going to use f of x. It's going to be about 1 to find the square root of 1.2. So I take all my derivatives. First derivative is, the actual function is square root of x. Then first derivative, second derivative, third derivative, fourth derivative, and I evaluate all these at the center. I get 1, 1/2, negative 1/4, 3/8, and negative 15 over 16. So hopefully that all makes sense. And then I've got my general form of the polynomial down here. Go out a little bit there. There we go. And there's the general form: f of 1, f prime of 1, f double prime of 1, f triple prime of 1, f fourth derivative, and then there's your factorials, and there's your powers up at the top that match the factorials. So there's Taylor formula. And then we can simplify it. There's your 1/2, negative 1/4, 3/8, negative 15/16, and there's your factorials. It simplifies to be this. So that's pretty straightforward. And then we want to find the approximation. This is all we have to do. The square root of 1.2, which is equal to f of 1.2, and that's approximated by this. So I just put this in my calculator. And then I just put 1.2. I var y vars it. You could actually write it all out if you wanted, but this is what you get. So there's your approximation. You can actually check that with the actual value to see how close you really are, and get your actual error if you want. Okay. Now let's look at the error bound. So this is the error bound, and again, it's going to be r sub 4. So I want the fifth derivative. Okay, and then at x minus 5, the absolute value of all that over 5 factorial. Remember, c, for this c, is going to be on the interval between a and x. My center was 1, and my x, my value, I'm going to evaluate this as is at 1.2. So I took the fifth derivative, and if you go back over here and you look at your fourth derivative, if you take the fifth derivative, and negative times the negative is positive, you have 7 times 15 over 2 times 16, 32, x to the negative. Subtract 2/2 is negative 9/2. So this was actually your fifth derivative, 7 times 15 over 32, and then that's x to the 9/2 on the bottom. And again, this is decreasing as x gets larger. The denominator gets larger, but the whole fraction gets smaller, so this is decreasing. So this is going to be bounded by m. I'm going to call m 7 times 15, 32 times 1 to the 9/2, which is just 7 times 15 divided by 32. Okay, so this is my error. X minus 1 to the 5th over 5 factorial. Now I've got to bound this. Now, since x is increasing on this interval, and x is in front, so if I got 1 minus 1, I get 0. If I got 1.2 minus 1, I get 0.2, which is bigger than 0, so it looks like it's in, but that's going to be the number I want. They're usually the endpoints. So you could choose the endpoint, and you know that it's going to max at that. So there was the value that we're going to use for the x. And so we use this for the derivative, which is decreasing, but use this for the x, which is increasing. And there you go. So this becomes just 0.2 to the 5th over 5 factorial, 7 times 15 over 32. Then we did a little arithmetic. You could put this in your calculator like that and crank it out. But 7 times 5 times 3 is 15, 32, and then 2 to the 5th. And then we could cancel the 5s and the 3s, so we end up with 7 on the top times 0.2 to the 5th. It's just that 0.2 to the 5th. And 32 times 8 is 256. Okay. 64, 128 times 2 is 256. And then you can work this out in your calculator quite easily, and that's your error. 8.75 times 10 to the negative 6. So that was 3. Okay, and let's take a look at 4. And 4 was just the sign of 0.2. So 0.2 is pretty close to 0, so I could use the sign of 0. I could use sine of x about 0, so I let f of x be equal sine of x about a equals 0. And then we've done these before, so you can take your derivative, or you can just use your Maclaurin series. You should know it by memory. Anyway, but I just worked it out. F of x, f prime, f double prime, f triple prime, and I put 0 in. I got 0, 1, 0, negative 1. And this simplifies real fast, so I kind of didn't show all the steps here, but this is 0, so my first term goes to 0. This is 1, so that's just x. This is 0, so it goes to 0, and this is negative 1, so it's just negative x cubed over 3 factorial, which is 6. So there was your a part. That was your polynomial. All right, and then I just evaluated it at 0.2, so I just put 0.2 into the function here, and you put 0.2 in here, you get that. 0.19867. All right. And now we want to find the error. So my fourth derivative is going to be just the sine of x, but if we look on this interval, and my interval is going to be, my center is 0, and my x value that I'm evaluating is at 0.2. So that's my interval 0 to 0.2. If I looked at the derivative of the sine, it's increasing anyway. But the problem with these things is the only way I could actually find the right endpoint is actually use the sine of 0.2. So I don't want to use the sine of 0.2 to find the sine of 0.2. That kind of doesn't make a lot of sense. So I'll have to settle for an error bound that's not as accurate as it could be, because I don't want to go back and if I could find the sine of 0.2 to find the error, why would I use an approximation in the first place? So it doesn't make sense to use the sine of 0.2. So we know that the sine and the cosine and all those derivatives will always be less than 1. So we're just going to bound this by 1. So we're going to let m equal 1. And that's what we usually do on the sine and the cosines. Just let m equals 1. And that gives us a good, clear error bound that we know without having to, use what we're trying to find. So I could just say that my r sub 3, which is that to the 4th over 4 factorial, the x to the 4th over 4 factorial, is just less than this. I just put 1 in there. And then on this interval, this is increasing, so the absolute value of x will be largest at 0.2, so I just have 0.2 over 4 factorial, and this calculated to be this, so that was your error. Okay, so that's a situation. And again, for the sine and cosine, we usually use just 1, because we know that those functions are naturally bounded by 1, and their derivatives are always each other, so that takes care of that. Okay, hopefully that helps. Now, I checked this just for fun, like I do. I've got it around here somewhere. And I actually checked the error that you would get, the actual value to the error. And I guess I can't find it now, but if I can find it, I'll find it. Nope, can't find it. I actually checked it, and you do get a better error when you use the sine of 0.2, obviously, but that doesn't really make a lot of sense. Okay, so there's your Lagrange error bound. That would be more traditionally used. Hope that helps.